Alright, so this week we're going to be taking a look at Chapter 5. So we pretty much do the whole chapter in 1 week, but it's because we only do 2.5 sections out of all 5 of the sections in the chapter. So we're going to look at 2 kinds of functions. The first one we're going to look at is exponentials. And when we get to 5.4, we're going to look at logarithms. Okay. So let's first just graph these 2, okay, and look at the difference. Okay, the first one is x squared, and the second one is 2 to the x. Okay, and they're going to look very different. So I'm going to type in x squared. So remember, x squared, that's just a parabola. It's the parent function for parabolas. It's the simplest parabola you can have. There's no shifts, there's no stretches. It's just x squared. And 2 to the x. So in that one, what we've done is we've switched the x and the 2. And let's do zoom 6. So the first one you can see, there's your parabola. And the one in red is 2 to the x. And if I go up a little bit higher, you'll see something that I'd like you to see. So x squared does curve up pretty fast. But if you look at 2 to the x, eventually the red one, it starts curving up even faster. Okay, you're just starting to see it. Okay, there is a little bit of time where x squared does kind of get above the red one, but eventually the red one, think of it, it kind of wins out. Okay, it's going to be much steeper. And if I go high, let me go a little higher. See it better. So there's x squared again, and here's 2 to the x, and you'll definitely see it getting steeper faster. Right there. Okay. The other thing is 2 to the x, it's not symmetrical like a parabola. It comes down, gets very flat. It gets close to the x-axis, but it never touches it. Does anyone remember what you call that? A graph that gets very close to something, but it never reaches it? It has a asymptote. Yep, or has an asymptote. Yep. And that's exactly what's happening with the red one. It has an asymptote. So in each case here, we have a base and we have an exponent. With x squared, the base is a letter, and the exponent is a number. Whenever you have something that has a base as a letter and an exponent as a number, that's the kind of functions we studied a lot in chapters 2 and 3. Okay, those are polynomials. But when you switch it and you put a letter as the exponent, that makes it exponential. So there has to be a letter in the exponent. There also has to be something else I'll talk about in a minute. Any question on the difference between the 2? Right, so that's what I just said a minute ago. That's the kind of things that we studied a lot in chapters 2 and 3. What? Chapter 2 was on quadratics, and chapter 3 was on all polynomials in general. When you have a variable in the base, and the exponent is an integer that's not negative, that's a polynomial. Now I said to be exponential, one of the conditions is you do have to have a variable in the exponent. But there is something else. You've got to have a variable in the exponent, but the base also has to be a positive number. But it can't be 1. Why do you think it can't be 1? Like if I wrote this down, 1 to the x.
Just x.
Why do you think that's not exponential? It's got a variable in the exponent.
Because 1 times anything is 1.
Right, well, if you keep multiplying 1 by itself over and over, you would just get 1. So 1 to the 10th power is 1. 1 to the 50th power, it's still 1. That would be a horizontal line. That's all that would be. Okay, so two conditions to be exponential. You've got to have a variable right there, and you've got to have a positive number. You can have fractions and decimals, that's fine. But it just has to be a positive number except 1. And that makes it exponential. Okay, let's bring that picture back up. And let's focus on just the graph in red. Okay, ignore the graph in blue. How far to the left do you think the graph in red goes? Goes to negative infinity. It just keeps going to the left. And how far to the right do you think the graph in red would go if you zoomed out? It would go to positive infinity. It goes up a lot faster than it goes to the right. But this graph will keep going off to the right. What do we call, what's the word that we use to describe how far left and right the graph goes?
Shift.
So this describes like all the numbers you're allowed to plug in for x. Domain, yep. So when you're dealing with an exponential function, the domain is all real numbers. Negative infinity to positive infinity. All right, let's look at the range. Let me get rid of the one in blue. Does it look like the graph in red goes up forever and down forever? No. It does do one of those. Which one?
Goes up forever.
It does go up forever, yeah. So in this particular function, I didn't write the range, but I can. The range is 0 to infinity. It never actually reaches 0. It just gets down closer and closer and closer to it as you head to the left. This can change. The domain does not change. So why doesn't the domain change? Well, it goes forever left and right. So if you shift it to the right a little bit, it still goes forever left and right. But if I do something like take 2 to the x, and just put like +3 on the end, I just changed the range. It doesn't go down to 0 anymore. Did anybody have a guess how low that it goes now?
3.
Yeah, it goes down to 3. So the range for that one would be 3 to infinity. So the range can change. Range change there. Domain never changes. So those are all just different examples of exponential functions. They all fit that definition when they have a letter as the exponent, and they have a base that is not equal to 1, and it's positive. What's the base in f of x? 10. Yeah, that's a positive real number. That's fine. How about the base in g? 4. It's a positive real number. And the base in h? Yep, pi. So the base can definitely be a fraction or a decimal, and pi is a decimal. These are all examples of things that are not exponential. The first one is not exponential because it does not have a letter in the exponent. It's got to have a letter in the exponent. Same thing with g of x. You got to have a letter in the exponent. It doesn't have that. And y, well, there's no letters in exponents there either. There's a fraction, but to be exponential, you don't need a fraction. You need a letter in the exponent. look at the difference between 2 to the x and 3 to the x. So let me get rid of that plus 3. Anybody have a guess what the difference will be?
How quick it goes up.
Yep, it's going to be how quick it starts to do that curve up. So here's 2 to the x. And then 3 to the x, you're going to see it start to curve up sooner. So it's going to be inside on the left of the red one. Right. So the bigger you make that number, the faster it starts to curve up. Right. And if you make that number a little smaller, like let's do, like 1.5 to the x, that's fine. As long as it's not 1, that's 1.5. That one's going to curve up slower. So it's going to be on the outside to the right of all of them. Okay, but those are all considered exponential functions. We can just change the steepness of the curve. All right. Now, what can be a little tricky to look at is when they throw a negative in the exponent. Right? So we need a way to figure out if they throw a negative in there, how can we get rid of it so we can kind of simplify what we're looking at. What's a to the negative first power? If you wanted to write that, it would be as a fraction. But I don't want to have that -1 as an exponent. You want to remember, what does it mean to raise something to the -1 power? Sure. Well, let's look at an example with numbers and see if we can then generalize what's going on. Let's take 2 and raise it to the -1 power. Here's 2 raised to the -2 power. Anybody see what's going on there? How could you raise 2 to a power and get 0.5? Think about, what would 0.5 be as a fraction? What is it?
Half.
A half. Yep, so this is a half. What's 0.25 as a fraction?
Quarter.
That's a quarter. So does anybody see how this turns into that? Yeah?
It's 1 over 2 squared.
Yeah, it's 1 over 2 squared. So when you have a negative exponent, this negative causes it to go to the bottom of a fraction. Okay? And same thing with this one. 2 to the -1. It's 1 over 2 to the first. So now, if we look at this, what do you think a to the -1 would be? Yeah?
1 over a.
1 over a. Yep. So anytime you raise something to a negative power, it makes it a fraction and it puts it in the bottom. And if you're wondering, well, where did the power go? It's still there. We just normally don't write it when it's just to the first power. All right, so let's look at this. So a to the -x. We're going to use this to help us get rid of that negative in the exponent. What number is always in front of a variable if you don't write it?
1.
You always have a 1. How about what number is in front of this variable because it has that symbol right there?
1.
Well, what does that symbol do to it though?
Makes it a negative.
Makes it a negative. So it's just like having a -1. Actually, let me do it like this. It's like having a to the -1 times x. And does anybody remember another rule from Algebra 1? If you had something like this, 2 cubed to the 4th power, it's 2 to something. Does anybody remember what you do with these two numbers?
You add them?
So you add them when you have something like this.
Do you multiply them?
Right, when you have something like that, you multiply them. Okay, when you have a power raised to a power, you multiply your two powers together. So, right here, we're multiplying two things together. So the only way that you could multiply two things together like that, so like what we have here, is really 2 to the 3 times 4. If you multiply two things together in an exponent, that means it must have come from something like that. You must have had a power raised to another power. So let's write that down. So we have a to the negative 1 to the x, power to a power. And then if we simplified it, we go back to this step where we multiply them together. The reason I wrote it like that is because we can fix that a to the negative 1. What did we just say up above a to the negative 1 is?
One over A.
1 over a. So anytime that you raise something to a negative power, if you want to get rid of this negative, which we do, all you have to do is take the base and flip it, and then the exponent becomes positive. So let's say I had something like, let's say 3 to the negative x. Anybody think they could tell me what that would be without the negative right there?
1 over 3 with,
1 over 3
x.
x is the exponent, yeah. Okay. Those two things are exactly the same. How about if I had something like 5 to the negative x?
1/5 what x is the exponent?
Yep, 1/5 with x is the exponent. And let me graph one of those so you can see that it does work. Let's do 3 to the negative x. And let me do 1/3 to the x. Okay, so 1/3 to the x. And if it does work, these should look identical. 1/3 to the x. Okay, that's still an exponential. It's just decreasing really fast rather than increasing really fast. And let's watch the new one. Yep, traces right over it. So 3 to the negative x and 1/3 to the x are the same thing. Okay. Any question on that? All right, so let's look at this. Okay, I want to graph each of those. How could we fix 2 to the negative x?
1/2 with x.
1/2 with what?
X is the exponent.
Yep, 1/2 to the x. And the reason why we want to do that is because if you look at each of these original, you may think they both have a base of 2. You say, oh, base of 2 means that it's going to look like that. It's going to look kind of flat on the left and then curve up. That's not really a base of 2 in the bottom one. It's really a 1/2. It's because this negative is messing up the base. So we always want to rewrite it so we get rid of that negative. That's kind of the point. All right, so let's graph them. And you already kind of see what it looks like, but I'll do it again. So let's graph 2 to the x. And when you graph the other one, you can type it in either way. I'm going to do it as 1/2 to the x. And then what we're going to look at is the domain and the range, okay, for each one. Also notice they look kind of symmetrical. Like if you flip it, the blue one would land right on top of the red one. And they are. They're mirror images of each other. Right, let's start with the domain. Okay. F of x is the red one. Actually, let me double check that. No, f of x is the blue one. It's the blue one. That's the red one. All right. What's the domain of the graph in blue?
Negative infinity, positive infinity.
Yeah, I told you that can never change. Okay, that never changes for any exponential function. How about the domain for the red one?
Same thing.
It's the same thing because it's a mirror image of it. Negative infinity to infinity. Okay, let's look at the range, up and down. How far up and down will the blue one go?
0 to positive infinity.
Yep. Do we ever reach 0?
No.
No. 0 to positive infinity. And how about the red one?
Negative infinity to 0. Oh, no, that doesn't make sense.
So when you describe the red one, think of the lowest it goes, and then comma the highest it goes.
Okay. Same thing.
It's the same thing, yeah. 0 to infinity. So they do look different, but they each have the same domain and range. Okay? The one in blue is what we call exponential growth, and the one in red is exponential. Anybody know the other term? It's the opposite of growth. Decay. Yep. Exponential decay. But they're both exponential. All right. So now we looked specifically when the base was 2. 2 to the x and 1/2 to the x. What I want to look at now is just kind of generalize it, where a can be anything. It doesn't matter if a was a 2, a 3, a 10. Doesn't matter. It could be any positive real number. All right. So these first two we're going to look at are going to have to do with the graph that we just did in blue. Let's look at the one in blue. So remember, this is a notation for saying as x heads to the right, as x heads to the left. As x heads to the right, as x heads to the left. So we're going to look at what happens as we go left and right on each graph you see on the screen. Okay, let's start with the blue one. So these two are going to be the blue, and these two are going to be the red. Okay. And remember, it doesn't matter if it was a 2 to the x, a 3 to the x, or a 4 to the x. It would just change the steepness of the curve, but the overall look would be very similar. So what happens in the blue graph as you continue heading to the right? What happens to the y value? So pretend like you're driving along the blue graph and you're driving to the right. What happens as you keep heading to the right? It increases. And what does it increase to?
Infinity.
Infinity, yeah. As you head to the right on the blue graph, you start to curve up. And you never stop. So you just keep curving up forever. How about as you start to curve, as you drive to the left on the blue graph? What does the y value get closer and closer to?
0.
It gets closer to 0, but does it ever reach it?
No.
Nope. That is the behavior of pretty much every exponential function. Doesn't matter about the steepness of the curve. Exponential growth, as you head to the right, it goes up. As you head to the left, it levels off at a number, like 0. Okay, how about the graph in red? What happens as you head to the right for the graph in red?
0.
It levels off at a number. In this case, it's 0. How about as you head to the left on the red graph? It goes up to infinity. Yep. Okay, so that's describing what we call the end behavior. What happens as you go to the right, and what happens as you go to the left. Okay, any question on that? So the key difference from a graph doing this to a graph doing this is whether the base is bigger than 1 or between 0 and 1. If the base is bigger than 1, you're going to get a graph that does this. The bigger you make it, the sharper the curve. If you do a base between 0 and 1, it's going to look more like that. The one on the left is called growth. The one on the right is decay. Okay, any question on the difference between growth and decay? So now let's look at transformations. I'm going to make a diagram just like we always do for every function. And I'm going to show you what moves it left and right, up and down, and what stretches it left and right and up and down. All right, so we have some base. Doesn't matter what your base is. That's not going to change how the transformations work. So we have so inside, you could take the base. You know what? Let me just do it for a specific number. I think it'll be easier than writing the word base. Let's say we had 2 to the x. You can add or subtract something inside. You can multiply by the exponent inside. You can multiply on the outside, and then you can add or subtract on the end. But remember, this can be any base. I think that's the easiest way to do it. All right, let's start with the A. Adding or subtracting, when I say inside, I mean in the exponent. What does adding or subtracting inside the exponent, what do you think that will do to your function? Do you think it'll be a shift or a stretch?
Stretch.
So stretch is always when we multiply. So that's a shift. And because it's inside, do you think it's going to be a horizontal shift or a vertical shift?
Horizontal.
That's a horizontal shift. Yep. Which way would plus move the graph? You gotta be careful. Remember, it's horizontal. Plus would move it left. Yep. And minus would move it right. Okay, so that's what A does. Let's do B. B is still inside, but it is multiplication instead of addition or subtraction. What kind of transformation is multiplication? Stretch. And because it's inside the exponent, it's going to stretch it which way? Horizontal. Yep. So that is a horizontal stretch. Remember, it is backwards. The bigger you make it, you might think, well, if I make B5, it stretches it 5 times as much. Nope, you're actually does it 1/5. So just as an example, if B is 5, it's a horizontal stretch by, just put that in a box right there. That'd be a horizontal stretch by 1/5. What do you think would happen if B was 1/3? Yep, that'd be by 3. Horizontal stretch by 3. So it's backwards. And one other thing B can do is if it's a negative. Anybody remember what multiplying by a negative number does to the graph? Yep. If it flips it, this would be a horizontal reflection or flip. So if B is negative, this is a horizontal reflection. So there's a little bit more to describe with B. C, kind of the same way. Now we're on the outside. What do you think multiplying by a number on the outside would do?
Vertical stretch.
Yep, that's your vertical stretch. It's not backwards. So if C is 4, it would stretch it by 4. So I won't do as many here. But if C is 5, it's a vertical stretch by 5. And what do you think would happen if C is negative?
Be a vertical reflection.
Yep, if C is negative, this is a vertical reflection. So remember, vertical reflection would look like this. That's vertical, flips up to down. And D, there's not a lot to it, so I think we can just kind of fit that one in right there. D is adding and subtracting, but it's on the outside. So what do you think D does?
Vertical shift.
Vertical shift. And it's not backwards, so positive, which way do you think that would shift it? Up. And negative?
Down.
Down. There you go. So that's a chart that describes all 6 transformations. In the order that you would do them in, I tried to explain with the A, B, C, and D. Start with your horizontal shift, then your horizontal stretch, then your horizontal reflection. Then you'd go to your vertical stretch, vertical reflection, vertical shift. That's the order. You generally will not have a problem with all 6. Maybe 3, 4, usually at the most. Okay, so take a minute and see if you can describe the transformations. I'll give you a hint, there are 3 of them. See if you can describe the 3 transformations it would take to turn this into that. And there are no reflections here. I'll tell you that as well. All right, so hopefully I had enough time to figure that out. We had 3 transformations. Can anybody tell me what the first transformation was here?
Horizontal shift left.
Yeah, we got that +1, so it's going to, we'll just say horizontal shift. You do have to say how much. Yeah, horizontal shift, left 1. Okay, what number are we going to focus on for the second transformation?
Vertical stretch by 2.
Yep, we're looking at the 2, and that's not backwards. So we just say vertical stretch by factor of 2. And we only have one number left, that's the -5. And what does that do?
Vertical shift down 5.
Yep, so shift down 5. Sorry. And that's it. Those are your 3 transformations. You'd never compare 2 functions that have different bases. Okay? You can't compare like something that has a base 3 to a base 4. They both will always have the same bases. Any question on the transformations? Or does anyone need to copy anything down from the diagram again? Or the chart? All right. Okay, so what we're going to finish up with is a few formulas that describe exponential growth and exponential decay. Right? So first of all, whenever something is exponentially growing, that means it is growing at a rate or a percent. So like if you worked at a job and you got a 2% raise every year, that is exponential. Okay? Over time, the amount of money you make will, well, very slowly start to curve up. Compare that to like working at a job and getting a raise of say $500 every year. That's different, that's linear. That's just an extra 500 every year. That's straight line. Okay, so whenever something is increasing at a percentage or decreasing at a percentage, it is exponential. So we're gonna look at a formula for exponential growth. And this is a formula that describes a population of a town that's increasing at a rate of r. Okay, there are 3 variables in it. The first variable is p. In this case, p stands for the initial amount. Okay, so p stands for the initial amount. R stands for the rate. And t is the amount of time. One thing you do have to be careful with the rate is it has to be a decimal. So for example, if they give you something that says a 12% increase, you have to write that as, anybody tell me what's 12% as a decimal? 0.12, yeah. So anytime you see a percentage, you need to change it to a decimal. 7%, 0.07. Right. T is the amount of time generally that is measured in years. Could be other things, but it's generally years. Now, if you change one thing in that formula, it changes it from exponential growth to exponential decay. Does anybody have a guess what the one thing that would change is? Yeah?
Like put a negative next to t.
No, the t actually would stay the same because t is the amount of time.
So turn 1 plus r to a fraction.
We do have to do something to 1 plus r, so we're on the right track. It won't be a fraction though. Anyone have another guess?
1 minus r.
Yep, it just turns into 1 minus r. Every other letter stays exactly the same. So you'd use 1 minus r if you had a word problem that said something like the population of a town is decreasing by 12% every year. Okay, so those are our 2 formulas for exponential growth and exponential decay. Now we'll try and does everybody have both formulas? All right, so we've got a town with an initial population of 50,000 people, increasing. So right away, increasing tells you, is this growth or decay? This is growth. It's increasing at a rate of 2.5% per year. So they want us to represent that with a formula. And then we're going to graph the formula, and we're going to figure out when the population basically doubles, when the population reaches 100,000 people. Okay. So let's first write down the formula that we're going to use. I'm going to use A for amount. So we're going to have an amount of people as a function of time. And what's the first thing that came right after the equal sign in the growth formula?
Initial amount.
Well, I would have an equal sign like right there. Yeah, initial amount, which is how much?
50,000.
50,000 times 1. We can put the 1 and we can put the plus. What's our rate of growth as a percent?
0.025.
Well, as a percent, it's 2.5, but as a decimal, yeah, 0.025. So that's what we need, 0.025. And the exponent we need?
365.
Well, t represents the number of years that have gone by. Do we know how many years
No.
have gone by? No. So we can't, it's not like they said predict the population 5 years from now. Then we plug in a 5 for t, right? But since we don't know that, that's all we can do. Okay, so that's the first part, model with a function. Now we're going to graph that. So we're going to need 50,000 times, and what do you get if you simplify what's inside the parentheses?
1.025.
Yep, 1.025. You do have to use x as the variable when you're doing it on the calculator. All right, so we are starting with an initial population of 50,000 people, and it's never decreasing. So it doesn't make sense to look at anything lower than 50,000. It's going to go up from there. We want to know when it hits how much?
10,000. 100,000.
100,000. So let's do a little extra. 120,000. Now x is the amount of years that have gone by. Can x be a negative number?
No.
No. So let's put it at 0, and let's see if we hit within 35 years the amount of people that they want us to hit. Okay, so there's a graph of the population. It's a little hard to see it, but it isn't linear, it is curving. And we have to put a line in there at what number so we can see where it hits.
100,000.
We need a line at 100,000. Yep. Okay, so now we've got our population. We're going to mark at 100,000. What do you think we're going to do with those two? Yep, calculate the intersect. So second calc intersect. Because there's only 2 lines and they only cross in one spot, you just hit enter 3 times. Okay. So how many years is it going to take for the population to reach 100,000?
28 or more.
A little more than 28 years. Yep. So take about 28.07 years to reach 100,000 people. And that's how you figure it out. Okay, so you start with your formula, you graph it, and then you got to put in another line at the population, and that's it. Any questions on that one? When you're graphing, be careful about negatives. Negatives usually don't make sense because if one of them is time, you can't have negative time. Or if it's about people, you can't have like a negative amount of people. All right, so now let's look at a formula for bacteria doubling. This is exponential growth too. Okay, whenever something's doubling, that's exponential growth. It's just a particular kind of growth. If you started with 100 bacteria and 0 hours had gone by in your experiment, how many bacteria would you have?
400.
Yeah, it's the initial amount. After 1 hour has gone by, how many would you have?
200.
200. After 2 hours?
400.
400, and after 3 hours, 800. So if you look at the amounts, it's always what you started with times 2 to the number of hours that have gone by. So 2 to the third because 3 hours had gone by. 2 to the second because 2 hours had gone by. 2 to the first because 1 hour has gone by. So in general, that would be the formula in this problem. The initial amount times 2. You just have to tell me how many hours have gone by, and I'll fill it in. So now we might not always start with 100 bacteria. We could start with any amount. So that's why I just changed it to initial amount. But what always comes right after the initial amount, when you're dealing with something doubling, is a 2. Okay? You don't have to worry about the 1 plus r. Whenever something's doubling, just make it a 2. And the exponent is t divided by the length of time to double. So why is it t divided by the length of time to double? Well, in our experiment, the bacteria was doubling how often? Every hour. This exponent has to represent the number of times that it's doubled, not necessarily the number of hours that have gone by. In our problem, those two things were the same. If something doubles every hour, then after 5 hours, it doubled 5 times. But let's say you had something that doubled every 3 hours. After 6 hours have gone by, has it doubled 6 times? No. How many times would it have doubled after 6 hours if it doubles every 3? It would have only doubled twice. And that's what this exponent has to be. It's the number of times it's doubled. So if 6 hours have gone by and it doubles every 3, 6 divided by 3, that's how you get it twice. If the length of time to double is a 1, then you don't have to worry about it. 1 would, because then they would be the same. Right, so let's try this one. We've got 100 bacteria, and they're doubling every hour. When will we have 350,000? Okay, let's start with our formula that's A stands for amount. What's the first thing that comes after the equal sign in the formula where something's doubling? 100, and in general, what is the 100? Initial, whatever the initial amount is. When it's doubling, don't worry about 1 plus r. What always comes right after that? Always just put a 2, only if it's doubling. And then you put your variable, and you have to divide it by the length of time to double. What's the length of the doubling time?
Every hour.
Yeah, it's just every hour. So really, if you put a t, it would be fine, because it is doubling every 1 hour. Okay. So there's your formula. Let's graph it. So we've got 100 times 2 to the x. Any question why I'm not putting x over 1? It's the same thing. Okay. So this, again, t is time. So we don't want to go negative, so I'm going to leave it at 0. I don't think this is going to have to double 35 times. I'm going to try just going up to 15 times. Because you're starting with 100, you're doubling, it's going to get to 350,000 pretty quick. Maybe we'll go to 20. All right. What's the smallest amount of bacteria that we could have? 100. And we want to know when we reach how much?
350,000.
Okay, so let's go to 400,000. So I need to put a mark at what number so I can see it. 350,000. Okay, so there's your population. All of a sudden, the number of bacteria just Yeah, see, we definitely didn't need 20. Something's doubling. It's going to go up very, very quick. So it's going to take about 11.8 hours. 11.8 hours. And what's that 11.8 hours again? It's the amount of time for what to happen?
It'll reach 350,000.
To reach 350,000 bacteria. Yep. Another example of how quick something increases when it's doubling, if you forget exactly, but if you start with a penny and you double it, I think for less than a month, by the time you're done, you'd be a millionaire if it doubled every day. So you might think it's such a small amount, it doesn't go up that fast, but it really does. So that's doubling at once, 3 times, 4 times, 5, 6, 7, 8. So at 8 times, you're already at $1. 9, 10, 11, 12, 13, 15, 16, 17, 18, 19. So after 20 times of doubling, you're already at $5,000. So 21, 22, 23, 24, 25, 26, 27, yeah, 28 days, and you're already over $1 million. So it goes up very quickly. All right, and the last problem we're going to look at is the opposite of doubling. It's halving. So this is called half-life. A lot of times you see half-life when you're talking about like nuclear material, like it's the amount of time it takes for half of your substance to disappear. So let's say you had a nuclear reactor and you produced 100 pounds of nuclear waste today. If it had a half-life of 1,000 years, that means after 1,000 years, that 100 pounds you made today will now have 50 pounds. After another 1,000 years, you'll have 25 pounds. So it keeps going down, but it actually never goes away. There's always a little bit left. And what do you think would change in this formula? It's almost going to look the same.
It'll be initial times 1/2.
It's going to be initial amount times 1/2. Yep. So whenever you're doing a half-life problem, it is exponential decay. It's dropping down. But you don't have to worry about the 1 minus r. You always plug in 1/2. And the exponent is the same deal as what we did for double. Okay, so let's try this one. We're starting out with 5 grams of a substance, and it has a half-life of 20 days. That means after 20 days, you'll have how much left?
2.5 grams.
Of 2.5. Yep. So we're going to find a formula, and we're going to graph it. Let's do that first. Does everybody have the part above the formula? Okay, so find an algebraic representation of the problem. Again, A is just going to stand for the amount that you're going to have left, and T will be the variable that controls how much you have left. Ruben, what comes right after the equal sign?
The initial amount.
Yep. And in this case, how much are we starting with?
5 grams.
Yep, perfect. 5 grams. For a half-life problem, what always comes right after the initial amount? Yep, always just put in a half. And what is my exponent going to be?
T divided by 20.
Yep, it's going to be t divided by 20. So that way, when you fill in an amount of days, it'll automatically convert it to how many half-lives have gone by. If you fill in 60 days for t and divide by 20, you'll get 3. All right, so let's graph that, and then we can finish up and answer the last question. So we've got 5 times, if you want to do the fraction, it's easier than having to worry about, if you don't want to do the fraction, the decimal is easier than typing. Raised to the x over 20. And we're trying to figure out when we have less than how much? 1. So what's the most amount of material that we're going to have in this problem?
5 grams.
You're never going to have more than 5 grams. And you're also never going to reach what number? You'll never reach 0. If you keep taking half of 5, it's never 0. It just gets smaller and smaller. So that's good. It's definitely going to take more than 20 days. Because I just asked, how much would you have after 20 days? You'd have 2.5. So let's go out to 80 days, which would mean it cuts itself in half 4 times. Let's see if that gets us under 1. So you gotta get below here. Yeah, we're good. Okay, so what are we going to do now?
Intersect.
Find the intersect. So it's, okay, so that's the intersect. Now, how would we write the answer? When will you have less than 1 gram remaining? After day 46. So anything greater than 46 days. If you said, well, less than 46 days, that would put you over here. That's above 1 gram. You want to be over here. So anything after 46.4 days. So after 46.4 days. Okay, so any questions on that? So that's exponentials. So looking at the transformations, writing a formula that you can graph and then find an intersect. And then we also did, what else do we do? Transformations. Oh, and then looking at the end behavior, yep. Domain and range. All right, so those are the questions for tonight. You've got 10 minutes left. Remember, if we don't have class tomorrow, then we'll just skip the review day. But if you do the review, I'll give you 8 extra points on the test. Okay, so the review will be worth 8 points if you do it. If you don't do it, that's fine. It's not an assignment to do the review. If we have class every day, then we'll do the review together on Thursday in class.